Hi everybody, I'm Anita Dominic. In this video, we are going to solve the miscellaneous exercise of class 12th chapter 3 matrices. So, let's look into the first question. First question is, let A equal to a 2 by 2 matrix 0, 1, 0, 0. Show that AI plus BA whole raised to n is equal to a raised to ni plus n a raised to n minus 1 n a raised to n minus 1 ba, where I is an identity matrix of order 2 by 2. So here given is a matrix, a 2 by 2 matrix A, and we have to show that ai plus ba whole raised to n is equal to a raised to ni plus n a raised to n minus 1 ba, where I is the identity matrix of order 2. So we are going to prove this using the principle of mathematical induction, which you have already learned in your 11th class. So first of all, we are going to prove the result for n equal to 1. So the principle of mathematical induction is like this. That is, first we prove the result for n equal to 1. Then we assume that the result is true for n equal to k. Then we show that the result is true for n equal to k plus 1. If all this is proven, then we can say that the result is true for every positive integer n. So first of all, we take the statement. We assume the statement Pn as ai plus ba whole raised to n is equal to a raised to ni plus n a raised to n minus 1 ba. So this is the statement Pn. Now we are going to prove n equal to 1, that is P1, statement P1. That is, we substitute the value 1 to n. Then we get P1 as ai plus ba whole raised to 1 is equal to a raised to 1 I plus 1 into a raised to 1 minus 1 ba. That is equal to, we get a raised to 1 I is ai plus 1 into a raised to 1 minus 1. We know that a raised to 1 minus 1 is equal to a raised to 0, and the value of a raised to 0 is 1. So we can write it as, this term becomes ba. So we got ai plus ba whole raised to 1, or ai plus ba is equal to ai plus ba. So the statement P1 is true. Now we have proved that the statement P1 is true. So now we are going to assume that the statement Pk is true. That is, for the value k, the statement is true. So we can write it as, we assume that Pk is true. That is, ai plus ba whole raised to k is equal to a raised to ki plus k a raised to k minus 1 ba is true. We assume that Pk is true. That is, this statement is true. So next we are going to show that the result or the statement Pk plus 1 is true. So we have to prove that Pk plus 1 is true. That is, we have to prove that ai plus ba whole raised to k plus 1 is equal to a raised to k plus 1 I plus k plus 1 into a raised to k plus 1 minus 1. It becomes a raised to k plus 1 minus 1. So it is a raised to k. We have a raised to k plus 1 and plus 1 minus 1. So that becomes, that plus 1 and minus 1 get cancelled, and we get a raised to k. A raised to k ba. So this is what we have to prove next. So in order to prove this, we will take the left hand side, the left hand part. That is, we consider ai plus ba whole raised to k plus 1. So here the power is k plus 1, isn't it? So now we are going to split this power k plus 1 into k and 1. That is, we can write it as ai plus ba whole raised to k into ai plus ba. That is, we split the powers, the a raised to k plus 1, the power ai plus ba whole raised to k plus 1 is split into ai plus ba whole raised to k into ai plus ba whole raised to 1. So Here we can split it like this, and we know that ai plus ba whole raised to k is the statement pk. We have the statement. If we name, okay, so we can substitute ai plus ba whole raised to k as a raised to ki plus k a raised to k minus 1 ba. That is, we get equal to a raised to ki plus k a raised to k minus 1 ba into ai plus ba. So here we have substituted ai instead of ai plus ba whole raised to k. The result a raised to ki plus k a raised to k minus 1 ba, and the balance rest is ai plus b into ai plus ba. Now we will multiply the term by term. So then we get the first term a raised to ki is multiplied with ai. Then we get a raised to ki into ai plus a raised to ki is multiplied with ba. Then we get a raised to ki into ba. So the next term, second term, k a raised to k minus 1 ba is multiplied with ai. Then we get k a raised to k minus 1 ba into ai plus k a raised to k minus 1 ba is multiplied with ba. Then we get k a raised to k minus 1 ba into ba. So next step we can write. So the balance we can see here. So again this is equal to, we can write, consider the first term a raised to ki into ai becomes a raised to k plus 1. The power of a increases by 1, and identity matrix we get a raised to k plus 1 into I. So the next one is, second term is plus a raised to ki into ba. That is, it becomes a raised to k into b, and I into a becomes a. So a raised to, this term becomes a raised to k into b into matrix A, plus we have this term as k a raised to k minus 1 ba into ai. So here we can see that a raised to k minus 1 and here another power of a. So this becomes a raised to k minus 1 plus 1, isn't it? A raised to k minus 1 plus 1. Here we have got another one power of a. So a raised to k minus 1 plus 1. Hence the power of a becomes a raised to k. And hence we get it as plus k a raised to k b, and rest is a into a, I becomes a. So we have this term as k a raised to k b into a. So the last term is k a raised to k minus 1 b a into ba. That is, it becomes b square a plus k a raised to k minus 1 b square a square. So it becomes b square a square. So the thing we have to note here is that these terms a, b and k are all scalar quantities, and I and a are matrices. So when we multiply the two numbers a raised to ki into ai, we are just multiplying the scalars and multiplying the matrices. So here we multiply a raised to k into a, and it is multiplied with I into I. So we have already learned it from the properties of matrices. Matrix multiplication, scalar multiplication and matrix multiplication. So here we are multiplying a raised to k into b and I into a. So next in this term we are multiplying k a raised to k minus 1 b into a, and then it is multiplied with a into I. So in the last term it becomes a raised to k minus 1 b into b. That scalar quantity is multiplied with the matrix A square. So hence we get this result. And now here we can simplify it as a raised to k plus 1 I, a raised to k plus 1 into I, plus here if we look the second and third term, we can see that a raised to k b a is common here, isn't it? A raised to k b a is common. So we can take it out. A raised to k b a into, it becomes, inside the bracket it becomes 1 plus k, isn't it? We can take out a raised to k BA outside. Then we have 1 plus, here there is left one k. So we have 1 plus k. So balance term is plus k a raised to k minus 1 b square a square. So if we compare this result with our required result pk plus 1. So we can compare it with our required result. That is, we have to get it as a raised to ai plus ba whole raised to k plus 1 is equal to a raised to k plus 1 I plus k plus 1 into a raised to k ba. If we look here, we can rewrite it once more. Then we have a raised to k plus 1 I plus, we can write this term as k plus 1 into a raised to k ba. Just interchange it. So we get a raised to k ba. So plus k a raised to k minus 1 b square a square. So now comparing it with our required result, we can see that there is an extra term. This is the only extra term left. So we will just compute the value of a square in this term. We will consider the term a square. So a square is equal to, we know that a is 0, 1, 0, 0 into 0, 1, 0, 0 is equal to, we get it as 0 into 0 plus 1 into 0 is 0, and next is 0 into 1 plus 1 into 0 is again 0, and in the second row first element 0 into 0 plus 0 into 0 is 0, 0 into 1 plus 0 into 0 is 0. Hence we got a square as a 0 matrix of order 2. So here if we look, since a square is a 0 matrix, the entire term becomes a 0 matrix. So the 0 matrix is multiplied with a scalar. Hence we get it as again as a scalar, again as a 0 matrix. So that this term is entirely becoming a 0 matrix. So we can ignore the, or we can just ignore the term. So this term is going to be a 0 matrix. Since a square is 0. A square is a 0 matrix. So hence we get the result as ai plus ba whole raised to k plus 1 is equal to a raised to k plus 1 I plus k plus 1 into a raised to k ba. This is our required result, pk plus 1. So we have proved that the statement pk plus 1 is true. So that is, the result is true for n equal to k plus 1. So hence by the principle of mathematical induction, we can say that the statement or the result is true for every positive n. Hence we can say that the result ai plus ba whole raised to n is equal to a raised to n I plus n a raised to n minus 1 ba is true for every positive integer n. So here we proved it by proved the problem using a principle of mathematical induction. For that, first we proved the result is true for n equal to 1. Then we assumed that the result is true for n equal to k. And then we proved that the result is true for n equal to k plus 1. Hope the problem is clear for you. So now we are going to the second question. Second question is, if A is equal to 1, a 3 by 3 matrix 1, 1, 1, 1, 1, 1. Each element of A is equal to 1. Prove that A raised to n is equal to a 3 by 3 matrix 3 raised to n minus 1, 3 raised to n minus 1, 3 raised to n minus 1, 3 raised to n minus 1. Every element is 3 raised to n minus 1. 3 raised to n minus 1. Okay. So, where n belongs to natural number n. So, given is a matrix 3 by 3 matrix A with each element 1. Each element of A is equal to 1. And we have to show that A raised to n is equal to a 3 by 3 matrix with each its element is 3 raised to n minus 1. So again we are going to prove this problem by using the principle of mathematical induction. So in order to prove that, first we consider the statement Pn as a raised to n is equal to 3 raised to n minus 1, 3 raised to n minus 1, 3 raised to n minus 1. So we consider Pn as a raised to n equal to a 3 by 3 matrix, which is with each of its elements as 3 raised to n minus 1. So we know that in the principle of mathematical induction, first we prove the result is true for n equal to 1. That is, we have to show that the statement P1 is true. So we can consider the statement P1. That is, in the place of n, we are substituting the value, we are giving the value 1. Then we get a raised to 1 is equal to, here we substitute 1 in the place of n, then we get 3 raised to 1 minus 1, 3 raised to 1 minus 1. So every element of a raised to 1 is equal to 3 raised to 1 minus 1. That is, it is equal to 3 raised to 1 minus 1 is 3 raised to 0, isn't it? So the value of 3 raised to 0 is equal to 1. So here we get every element as 1. We know that it is equal to the matrix A. So hence we get a raised to 1 is equal to A. So the statement P1 is proved. So now we have proved the result. The statement P1 is true. So now we are going to assume that Pk is true. We are going to assume that Pk is true, or the statement or the result is true for n equal to k. That is, we are going to assume that Pk, that is a raised to k, is equal to 3 raised to k minus 1, 3 raised to k minus 1. Okay, 3 raised to k minus 1, and the entire result is true. We are going to assume that the statement Pk is true. So next we are going to prove that the statement Pk plus 1 is true. We have to show that the statement Pk plus 1 is true. That is, we have to show that a raised to k plus 1 is equal to 3 raised to k plus 1 minus 1. We have 3 raised to k plus 1 minus 1. Each term, each element of the matrix a raised to k plus 1 is 3 raised to k plus 1 minus 1. And this plus 1 and minus 1 get cancelled, and we get it as 3 raised to k. The plus 1 and minus 1 get cancelled, and we get each element as 3 raised to k. So we have a raised to k plus 1 is equal to 3 raised to k, 3 raised to k. So every element of a raised to k plus 1 is 3 raised to k. This is what we have to show. This is what we have to show. That is, we have to prove that Pk plus 1 is true. That is, we have to show that the result is true. This is what we have to prove. So in order to prove that, we are considering the LHS, or a raised to k plus 1. We are considering a raised to k plus 1. So a raised to k plus 1 can be written as a raised to k into a, isn't it? We can write it as a raised to k into a by splitting the powers. So now we have a raised to k. We have assumed our result Pk, that is a raised to k equal to a 3 by 3 matrix. So we have assumed that this result is true. So we can substitute a raised to k with this matrix. Hence we get as a raised to k as 3 raised to k minus 1 into, 3 raised to k minus 1, 3 raised to k minus 1. Every element as 3 raised to k minus 1. So into a raised to k into a. So we can substitute a, that is a 3 by 3 matrix with each element as 1. Now we have to multiply this. Then we get, so hence we get a raised to k plus 1 is equal to the product of these two matrices, that is 3 raised to k minus 1 into 1 plus 3 raised to k minus 1 into 1 plus 3 raised to k minus 1 into 1. So if we see here, we can see that 3 raised to k minus 1 is added 3 times. So the first element is 3 raised to k minus 1 is added 3 times. That is 3 raised to k minus 1 plus 3 raised to k minus 1 plus 3 raised to k minus 1. So we can write, since 3 raised to k minus 1 is added 3 times, we can write 3 into 3 raised to k minus 1, isn't it? So we can write it as 3 into 3 raised to k minus 1. Similarly, the next term becomes, second element becomes 3 raised to k minus 1 into 1 plus 3 raised to k minus 1 into 1 plus 3 raised to k minus 1 into 1. Again we get 3 into 3 raised to k minus 1. Similarly, we can prove that every element is 3 into 3 raised to k minus 1. We can prove that every element is 3 into 3 raised to k minus 1. So, we have seen that if the product of these two matrices is a 3 by 3 matrix with each element as 3 into 3 raised to k minus 1. So, if we consider one single element 3 into 3 raised to k minus 1. So, here we can say that 3 into 3 raised to k minus 1 is 3 raised to 1 into 3 raised to k minus 1. That is equal to 3 raised to 1 plus k minus 1. Isn't it? The powers get added. Okay, so we can write it as 3 raised to 1 plus k minus 1. So, here the plus 1 and minus 1 get cancelled. 1 minus 1 gets 0. So, we get it as equal to 3 raised to k. So, 3 raised to 1 plus k minus 1 becomes 3 raised to k. That is, here each element becomes 3 raised to k, which is equal to 3 raised to k, 3 raised to k, 3 raised to k. So, we got a raised to k plus 1 as a 3 by 3 matrix with each of its elements as 3 raised to k. So, is this what we had to prove, isn't it? We had to prove that the statement pk plus 1 is a raised to k plus 1 equal to matrix, a 3 by 3 matrix with each of its elements as 3 raised to k. So, we had proved that. So, now we had proved that a raised to k plus 1 equal to the required matrix. So, we have proved the result for n equal to k plus 1. Hence, by the principle of mathematical induction, we can say that the result is true for every positive integer n belongs to n. So, first we proved that the result is true for n equal to 1. Then we assume that the result is true for n equal to k. Then we have proved the result is true for n equal to k plus 1. Hence, by the principle of mathematical induction, we can say that this result is true for every positive integer n. So, hope you are clear with this question.